first I'm going to give you a little bit of motivation why we need to consider systems of differential equations, right? We'll go through two examples of modeling with systems of differential equations, right? So in the first example, we have three tanks. Well, it is a bit strange, I know, but anyway. So there is a pipe from outside into the first tank, and there is a pipe from the outside into the second tank, and sweet water is flowing in. And also that there is a pipe to the outside, another pipe from tank 2, and whatever the mixture in tank 2 is flowing out. And at the same time, there are pipes between tank 1, tank 2, and tank 3, and the mixture is moving between the tanks. And the rate of each flow is given here. The question is to set up a mathematical model of how much sugar we're going to have in each tank after a certain period of time. All right, now, if we look at each tank, then suppose that we just look at tank 2 or whatever, right? So then suppose that x of t is the mass of sugar in this tank at time t. Then the rate of change of the amount of sugar is basically the rate of change from new sugar coming in minus the rate of change from new sugar coming out, right? So rate in minus rate out. But the rate is going to be the concentration of the sugar in the flow in grams per liter times the intensity of the flow in liters per minute. Also, you can check carefully that the total amount of mixture in each tank remains the same, because the total inflow equals the total outflow for each tank. That's easy to verify. All right. So now, if we have three unknowns, which is the amount of sugar in each tank, then let's look at the first tank, right? So there is a pipe from the outside. So we have the rate of change of sugar gives us the positive summand, 30 times 10, because 30 was the concentration in the pipe that goes from outside, and 10 liters per minute is the intensity of the flow. That's how we get 30 times 10 for the dx1 over dt. Right? So then another source of sugar in the first tank is from the third tank. So there are two sort of channels coming in and one channel going out from the first tank to the second tank, right? So then if we look at the second tank, then again there is some sugar coming in from the outside. There is some sugar coming in from the first tank. Yeah, and there is some sugar going out to just the outside, and there is some sugar going from the second tank to the third tank, but it doesn't matter, of course. I mean, it just leaves the tank, so we combine them together and put the minus sign. And for the third tank, there is a sugar coming from the second tank. Yeah, and there is a sugar going to the first tank. So, for example, let me maybe highlight it, that if we look at this number, this is sugar leaving the first tank, and this is sugar coming in the second tank from the first tank. Right? And say this number, so this is sugar coming in from the first to the first tank from the third, and this is sugar leaving the third tank to the first tank. So of course they have to be consistent. But here this is sugar that goes to the outside world and to tank 3. So that's why this coefficient, this term is not the same as this term, because this term only counts sugar from tank 2 to tank 3. Right, so but then we can write it in the vector form or in the matrix form. So notice that the matrix of coefficients here is constant. So it is, we are going to get a linear system with constant coefficients. But because of the right-hand side here, it is non-homogeneous. All right. That was my first example. It is a bit artificial, I know, but imagine that instead of tanks, you want to model how imagine that there is some kind of complicated chemical factory with really a lot of tanks, and there is some leakage, some poison leaked out into the system, and you want to find out how much poison is going to be, or maybe some radioactive substance. So in order to be able to model these things, you kind of can consider it as a system of interconnected tanks with really a lot of tanks. So, and the basic idea is going to be the same, of course. All right. Now my second example set up a system of differential equations that models the motion of a planet around the sun. Right. So we are going to use the Newton's law of universal gravitation. And according to the law of universal gravitation, the acceleration is inversely proportional to the distance from the planet to the sun. Right? So suppose that, of course, the Earth is moving. Strictly speaking, it is in the 3D space, but of course, Earth is going around the sun in within a plane. Right? It's called the plane of ecliptic, I think. Well, it doesn't matter. So the whole thing happens in the 3D space, but the actual motion is only two-dimensional, right? So that's why I can put the origin at the sun's position, right? And then suppose that x and y are coordinates of the Earth, so as functions of t. All right. So then the distance is going to be square root of x squared plus y squared. So acceleration as a scalar, that's acceleration from Newton's law. But that's a scalar. But of course, what Newton's law tells us is that the magnitude of acceleration is this number. Right? I'm sorry. Magnitude of acceleration is this number, but the direction of acceleration is, of course, just towards the body that that exerts the gravitational force, right? So acceleration vector is going to be proportional to xy, and it is going to be proportional to xy, but its magnitude is going to be equal to a. That's how I got this formula. And therefore we get these equations. So notice that this is a system of second-order differential equations. It is nonlinear. It is autonomous because the right-hand side does not include t. But let me do a little very neat trick, right? So I'm going to introduce two new variables, right? I'm going to write it u equals x prime and v equals y prime, right? So if u equals x prime and y equals and v equals y prime, then what is going to be u prime? So u prime is going to be x. U is x prime, and u prime is x prime prime, so which is x double prime. So the first derivative of u is the second derivative of x, and that's how I get this, and this is of course going to be v prime. And now just look at this part and look at this part, right? So it means that by introducing these new variables, we reduce the order of this system. So we introduce 2 more equations, but at the same time we reduce the order. So whenever we want to reduce the order by 1, we can do it by introducing 1 more equation to this system, right? So again, that is very important. So we have converted a system of 2 second-order equations into a system